Okay, in this podcast we're going to talk about quantum mechanics. So quantum mechanics picks up where Bohr left off and actually brings us to where we are today in terms of what we believe about the atom. Now, while a lot of things that Bohr said we still believe today, his model only worked for the hydrogen atom, and others realized that his model wasn't sophisticated enough to describe what's going on with electrons in all atoms. Okay, so let's take a look. So this is the quantum mechanical model. We often will call it the QMM for quantum mechanical model. And it is a model based on probabilities. So if you think about all these little dots in here, they represent a probability map of where electrons are most likely to be located. Okay, and the model comes about based on work from a lot of scientists, but principally Werner Heisenberg and Schrödinger. And yes, Schrödinger does have a cat. Okay, Heisenberg's contribution to the quantum mechanical model is known as the Heisenberg uncertainty principle, which says that it's impossible to know both the location and speed or velocity of a particle at the same time. So let's talk about why that is. I'm going to show you an animation. We're going to watch it all the way through, and then we're going to come back and talk about it. Okay, so what we have here is we want to use viewing, be it a microscope or an eye, anything that's going to view where something is located or be able to identify its speed requires light in order to be able to see it. And in order to have light, that light itself has energy, and it's in a wave, right? So just the process of looking at the electron causes it to move, and therefore causes a change in the wavelength that comes out. So this, in order to identify where an electron is, you need to be able to interpret the light it emits when it comes off. So you really can't do that in a way that tells you both the location and velocity, which is why this is a probability model. We cannot know exactly where an electron is at any time, but we can say where it is most likely to be. Okay, Schrödinger put together a complex mathematical equation that can be solved in order to identify the location of electrons within an atom. Now, we're not going to use this equation, you're probably relieved, but if you take quantum mechanics in college, you will, and you will actually create plots of where the electrons are likely to be located. And when you do that, what you end up with are these locations, these maps of where the probability of finding an electron is. And you probably recognize it, S, P, D, and F. We've talked about those in the first year chem. Okay, so if you solve Schrödinger's equation, you end up with a unique address for each and every electron. And there's a rule that when we get to electron configurations called the Pauli exclusion principle that says every electron has a unique address and allows me to identify exactly where it's located. And we do that using these 4 different quantum numbers. So if you think about an address, let's say 10 South Street in Philadelphia, PA, this would be analogous to the first quantum number. It tells me the general location. A little more specific, that's my second quantum number. My third is the street name, and then the fourth would be the exact house on that street. That's the way quantum numbers work. Okay, so if you look at the different quantum numbers, the first is known as the energy level, and this looks a lot like Bohr's model. And you might say to yourself, well, why does it look like Bohr if we no longer believe Bohr? Well, in fact, there's a lot of things about what Bohr said that we still believe. And that is the whole idea about energy levels. We still believe there are different quantized energy levels at different distances around the atom. Okay? The difference is that Bohr said electrons can be here or here, but they could not be here. And what Schrodinger and others said was that electrons can be anywhere, but we can define the probability of where they're more likely to be located. And in fact, they're more likely to be located on these n equals 1, n equals 2, okay? So, the closest to the nucleus, the first shell where an electron could be found is n equals 1, and then it works its way out, 2, 3, and 4. Okay. The second address piece tells what shape orbital, sp, d, or f, the electrons are located in. The third talks about the orientation. So if I think about a p orbital, a p is like a dumbbell or a figure 8. Well, in fact, I have 3 p orbitals at each energy level, and the 3 are on 3 different axes, x-axis, y-axis, and z-axis. Okay, so it's the orientation of that axis. And then the last is spin. So the belief is that any orbital can have 1 or 2 electrons. And if there are 2, they will have opposite spins. And we usually show those spins as an up arrow and a down arrow, but sometimes we show them as a plus 1/2, minus 1/2. So if you think about oxygen's orbital notation, these are the 8 electrons of oxygen. If you think about each one of these, they have a specific set of 4 quantum numbers, or 4 things that tell us where it's located. So let's identify where this one is located. So the principal quantum number is going to be 2. It's in the second shell, shown by this. The second number, so this is the first quantum number, the second quantum number tells me it's a p orbital, right, defined by here. The third, now I can call this p sub x, p sub y, p sub z on the orientation, right? So I would call that a p x orbital, okay? And the fourth is the spin, and the spin is up, okay? And there is no other electron in oxygen that has the same set of 4 quantum numbers, okay? If I look at this electron, it has a downspin, okay? So they are different. So the quantum model of the atom says that there is a tight central nucleus, tiny, tiny, tiny in terms of volume compared to the rest of the atom, and it's surrounded by a very large electron cloud in comparison with the electrons located in these orbitals. These s and p and d and f are orbitals. So why does this even matter, right? Well, if you think about each of the subatomic particles, the proton determines the identity of an element. So if I am an element, an atom with 8 protons, I am an oxygen atom, right? If I have neutron, it determines the mass of the element or contributes to it. But the electron is really the workhorse of the element, and it's responsible for the reactivity, whether or not an atom is going to react. And if it does, what it reacts with and how vigorously and all that other stuff. So during defining the location of the electrons in the atoms helps us understand their reactivity with other elements. Okay. So let's go back. You do need to know what's called the principal quantum number, which we call n. We talk about n a lot, and n describes the energy level again. We often, synonym for this is shell. We'll say which shell is it in. And one of the really nice things is if the electron is located right in here, that corresponds, this is to the periodic table, the first row, or the first period, n equals 1. So if I'm putting an electron in here, in n equals 1, it goes in the first period. If I have n equals 3, then I am down here third row of the periodic table. Pretty neat. All right, the second thing, you don't need to know what the numbers are that go with these, but you need to know what an S, a P, a D, and an F. You need to know what the shape of an S and a P are. But it's also convenient that here we have this periodic table. We have, this is the S block. If I'm adding an electron here, they're going into an S orbital, right? The S orbital. If I'm adding electrons here, they're going into a P orbital. If I'm adding over here in the green section, it's going into a D. And of course down here would be F. So by looking at the periodic table, I can tell a tremendous amount about where those electrons are located. Okay, so an S orbital you need to know is spherical in shape. So if I think about an atom that has multiple energy levels, it's going to have an S orbital, a 1s, n equals 1. And then it will have the same shape, but it will be larger. It will be on top of the 1s, and the 3s will be on top of the 2s, which is on top of the 1s. P orbitals, again, some people call them dumbbells, figure eights, whatever you want to call them. This is what their shape is, and there's a different orientation for each.